This is section 2.7, the unit vector. So where we have been, or what we've been doing here, is trying to come up with vector descriptions of forces in Cartesian, using the Cartesian coordinate system, using Cartesian units. And if you recall, this is from review. If the angles are specified, then we would use the alpha, beta, gamma method. If the ratio is specified, then we'll use the ratio method. If the angle is given as a relative to a plane, then we can use the f prime method. And if the distances are given, then we're going to use the unit vector method. So if you can see in these two problems, or these two pictures, that there are no angles specified, but however there are some distances. So with the unit vector method we can come up with Cartesian descriptions of these forces. Well, what is the unit vector? It is a way of describing the direction of a vector. So let's say that we have a point out here in space. Let's say it is 3 in the I direction and 5 in the j direction. We can draw a vector. We'll call it A. We know that there are components along the x-axis, AX, and a component on the y-axis, AY. The vector description of that vector, or the Cartesian description of the vector, is 3i plus 5j. We can find the magnitude, or the length, of that vector by taking the square root of the sum of the squares. In other words, square root of 3 squared plus 5 squared, and we'll get that magnitude. The unit vector is defined as the direction only, which is the vector divided by the magnitude. And I'll call the vector with an A bar and the magnitude with perpendicular bars or parallel bars, vertical bars on each side of that vector. So the unit vector then, if you just write it out, it's going to be 3i plus 5j divided by the magnitude. Multiply out the magnitude on the bottom, divide each of the components by the magnitude, and you get this vector description of the unit vector. And again, that is only the direction, and you can see that both components of I and j are less than 1. And so when you get a unit vector, just make sure that both components are less than 1, and then you'll know that you're probably on the right track. If A was a force, let's say that it's equal to 100 newtons, then the force of A is defined as F magnitude times the unit vector. So in this case, the magnitude of the force is 100 times 0.515 I plus 0.857J. Now again, so that's a good vector description, F mag times unit vector, but you can also multiply it out. So that would be 51.5 I plus 85.7 J. And now that would be the vector description of the force that is along that line. Alright, what about if the vector does not begin at the origin? Is there any difference? So let's say instead of originating at the origin, it originates at that point. We're still going 3 in the I direction, 5 in the j direction. What's the difference? Let's say it's still 100 newtons. Is there any difference? Well, remember that a vector is defined by the magnitude and the direction. So in this case, the direction is the same, the magnitude is the same, therefore the vector is the same. The force vector is the same, so there's no change in the vector. So it doesn't matter where the vector starts. Any vector can start at any point and it'll still have the same definition. Now, position vectors are useful when we're going from one point to another point. So let's say that we have a point out here. We'll call it A, and let's say it is 8 in the I direction and 7 in the j direction. We may have another point over here, B, and it is -2 in the I direction and positive 2 in the j direction. We can draw vectors A and B if we wish. So let's just draw those there. I'll call that A and this B. The position vector between A and B is defined as from A to B is B minus A. And that'll be vector AB. So let's just go ahead and mark it. This will be AB from A to B. We'll call that vector AB. And the way we get there is we take vector B and we subtract vector A. So that's what I've done. Negative 2i plus 2j, and then 8i plus 7j. And I'm going to say negative 2 minus 8 is negative 10 in the I direction. Positive 2 minus 7 be negative 5. So that would be the vector description of AB. And let's just draw the components of that and just see if we're right. I'm going to go down this way and over this way. And if you count those out, this will be negative 5 in the J direction. And this will be negative 10 in the I direction. And that will get you from A to B. We can find the length of that vector by taking the square root of the sum of the squares. That would be 11.8. We can find the unit vector of AB by taking the vector description of AB, divide by the magnitude, and divide that out, and you'll get the unit vector of AB. Well, we're going to talk about three-dimensional vectors now, and I encourage you to buy one of these isometric notebooks. You can find them at the bookstore or on Amazon. It only costs a couple of bucks, but it helps to draw three-dimensional forces, and we'll be doing that as we go forward. On your homework, I will give you a copy that you can print, I suppose, if you wish, but I encourage you to buy your own. That way the lines will be very clear and you can use it for your advantage. Well, let's do a 3D vector here, a three-dimensional vector. So I've got some points defined on my 3D axes here, and I'm just going to draw the vector and kind of show you how you go about assembling the components. But let's say we have something, say we go 2 in the I direction, and 1, 2, 3, 4, 5, 6 in the J direction, and 1, 2, 3, 4, 5 in the K direction. If we define those points and then kind of connect the dots, so I'm just going to connect those dots, and you can see what the three-dimensional, it looks like I missed one of the points here, or whatever, and then we'll do that. It doesn't really matter if it's perfect, but you can kind of connect the dots here and you can see where this vector might occur in space. So this is my point that I'm going to, and I'll call this vector A, or I call it vector F. So let's find the vector description of F. So F is going to be F mag times the unit vector. And if we say the magnitude is 100, let's go ahead and put that in there then. This will be 100 times 2 in the I direction, that's going to be this component, plus 5 in the J direction, actually 6 in the J direction, plus 5 in the K direction. And divide that by the square root of the sum of the squares. Multiply all that out, you get 100 times 2 over 8.06 I plus 6 over 8.06 J plus 5, 8.06 K. And then you can multiply all that out if you wish, or if it's required. So I'm going to divide those. Now this portion here is the unit vector. That portion is the unit vector. This is all the unit vector here. Now once we multiply it out, it's not the unit vector anymore, but it is the actual Cartesian description of the force. So let's just do that. Alright, so there we have. That's the vector description of the force, and you can see how easy that is. And again, I like using the vector box on 3D graph paper, and it makes it pretty simple to do. Well, I want to find a three-dimensional position vector now. So I have a couple of spots defined here. The first spot, A, is on the XY plane, and I'll call that 4, 3, 0. And then there's spot B over here, which is on the YZ plane, 0, 7, 7. Now, if I want to find the position vector from A to B, I would just draw that straight like that, and that would be vector AB. And how do we calculate all the things there are to do about that? In other words, to find AB, we would subtract from B, or from A to B would be B minus A. And so I've calculated that out for you. AB is equal to B minus A, and just subtract them all, and you get a vector description, a Cartesian description of vector AB. Now, how about the length and maybe the unit vector description of AB? What does that look like? So if you look at the length, that would be the square root of the sum of the squares. So it would be 4 squared plus 4 squared plus 7 squared from here. That's equal to 9. The unit vector then is equal to the vector, which is right here, divided by the magnitude on each term, and you get the unit vector right there. So we'll draw a box around there looking for the unit vector. So the use of the unit vector is handy. So here's a fundamental problem, and we'll use our concepts here to see if we can discover something about this. So what we have is a little board or stick leaning against the wall, and it starts here at point A and goes to point B, and the objective is to find the length and the angles relative to the major axes. You can see that there's one angle given here as theta, but it's an unknown. So let's define the vector AB. And what we've discovered is A to B is B minus A. However, there's a shortcut that can be used if it's easy, and if you can see the dimensions clearly on the picture, then just go from A to B. So I'm going to start here. I'm going to go from A, go that way in the I direction. So that would be -4 in the I, +2 in the J, and +4 in the K. When I do that, I get a vector description of AB, Cartesian description of AB. The magnitude is given by the square root of the sum of the squares, and I get 6. The unit vector is going to be the vector description of AB divided by the magnitude. So it's going to be 4 divided by 6 in the I direction, 2 divided by 6 in the J direction, and 4 divided by 6 in the K direction. So there's the unit vector. How about that angle? The angle alpha is the angle relative of the vector relative to the, or measured from, the positive x-axis. So in this case, theta is given, but that's in the negative x-axis. It's going in the negative direction. So the alpha is actually going in this direction. So it is 180 degrees minus theta, or theta plus alpha is equal to 180 degrees. So how do we find alpha? Alpha is AB in the x direction divided by the magnitude. So that would be -4. That's the cosine of alpha, -4 over 6. And then if you take the inverse cosine of -2/3, you get 132 degrees. So that's the angle alpha, which is with the positive x-axis. Then angle theta is 180 degrees subtracted from that. And we could find, similarly, we could find beta and gamma if it was asked for.